I'm here to describe to you a crazy idea that will revolutionize our understanding of the universe. Don't roll your eyes. This is not just empty theory, the mad ramblings of an old physics professor. The idea may sound crazy, but it has been put to the test many times in ingenious ways, and we all rely on it every day without even realizing it. Chances are that the new phone you got would not work properly if a young physicist who got his start working as a humble clerk at a Swiss patent office hadn't come up with a crazy idea in the early 1900s. General relativity is what makes GPS possible. Crazy ideas often fuel progress in science. Albert Einstein's original crazy idea was that gravity is not a force, but an artifact of space being curved. How can space be curved? Well, imagine placing a soccer ball on a rubber sheet. Clearly, the ball curves the sheet, and how much it is curved depends on the mass of the ball. The rubber sheet represents our usual three-dimensional space, and the soccer ball represents massive objects like our sun. If you now place a tennis ball on the sheet as well and let it be, it would roll down the rubber sheet towards the soccer ball, almost as if there was an invisible force pushing it. This is the basis of Einstein's crazy idea, the theory of general relativity. You don't need Newton's invisible and almost magical force pulling objects close to each other. You only need geometry. Crazy ideas usually give birth to other even crazier ideas. It's our job to push all of these crazy ideas to their breaking point. So let's imagine placing heavier and heavier objects on our rubber sheet. Instead of a soccer ball, let me place a bowling ball, and then another, and another, and another. The more balls I place on the sheet, the more curved the sheet becomes. So curved, in fact, that if you are sufficiently close to the center, at some point, no matter how much you try to climb out, you just can't. Einstein's crazy idea has led us to the concept of a black hole. Picture the sun. Roughly 1 million Earths could fit inside it. Now imagine that I compressed the sun, and little by little I made it smaller and smaller and smaller, eventually making it the size of a ball so small that it could fit in the Boston-Cambridge area. Because of its immense mass, the gravity produced by such an incredibly dense object would be almost unimaginable. Even before I had finished squeezing that star into such a small space, when I had gotten it as compact as, say, a neutron star, the density would be incredible. A teaspoon of such dense material would weigh about as much as Earth itself. As I squeezed further, the matter would become so incredibly dense and its gravity so incredibly strong that not even light could escape. An object so gravitationally strong that it prevents light from escaping defines a black hole. Why? Because if there's not light, there must be darkness. Now, imagine being magically transported inside a black hole. Scotty, beam me up! What would happen? Well, you would sink to the center, but how fast? Well, if the black hole had the mass of the sun, and if you were standing about 1 mile away from its center, you would be pulled to the center and reach the center, also known as the singularity, traveling at about 1/3 the speed of light. Can you imagine sprinting 1 mile at 1/3 the speed of light? That is 10 million times faster than Usain Bolt, currently the fastest sprinter on Earth. Unfortunately, you would be shredded to pieces before you reach the singularity. If instead of running toward it, you just dove into it head first, then your head would be pulled faster than your feet and torn apart. Okay, so that's a pretty gory image, but this is what Einstein's crazy idea led us to. So now you know enough about Einstein's crazy idea that I can describe to you the even crazier one that I mentioned at the very beginning of this talk. This crazy idea has to do with our rubber sheet and what happens to it if our bowling balls start moving. Perhaps the easiest way to picture this is to imagine, instead of a rubber sheet, a pond and a little toy boat in it. If we give the boat a little push, it will surely move on the water, but the water will also move. After all, for every action, there's an equal and opposite reaction, right? So the motion of the boat will produce ripples in the pond that will travel away from the boat. These ripples carry information about the boat. How fast is the boat moving? In what direction? What is its precise shape? Similarly, when black holes move, or more precisely, accelerate, they also produce ripples in our rubber sheet of space. For example, if black holes are in a binary system, orbiting one another, they produce ripples in space. These ripples travel away from the black holes in every direction, and some of them reach Earth. We call them gravitational waves, and just like the water pond ripples, they carry information about the black holes. How heavy are they? What do they look like? How fast were they moving? Questions that, in fact, we can't answer in any other way, since, after all, telescopes can't see objects that are black. Now, up until now, we've constructed an image of our universe just by looking at it through very powerful and incredibly sophisticated telescopes. These telescopes have shown us some of the wonders of the universe, like the remnants of giant stellar explosions that we call supernova. Telescopes have also been able to give us impressive images of our sun, our solar system, our Milky Way galaxy, and in particular, the galactic center. In fact, it's through such observations that we first inferred that telescopes can't see black holes per se, but they can see the effect of giant black holes on stars that are nearby. Giant telescopes in Hawaii and Chile have succeeded in imaging these stars and tracing their orbits. Based on this and some mathematics, we can calculate what the mass of the invisible central object about which all of these stars are moving must be. The math comes out to 4 million times the mass of our sun. But if such a big object were at the center of our galaxy, it would have to shine, and we would see it. However, when we point all of our telescopes at that point, we see blackness. This is why we say there must be a black hole at the center of our galaxy. But telescopes can't tell us the whole story. We're missing a very important ingredient: sound. Gravitational waves can be generated by objects that don't shine, and they travel through dust, matter, everything, almost without being distorted at all. As such, the unique information they carry reaches us with the ability to give us a true picture of the source, a picture that, in fact, cannot be obtained any other way. For example, they can give us a glimpse of how black holes spiral into each other in a catastrophic coalescence, a death dance of sorts. The detection of these gravitational waves would then not only verify Einstein's last prediction, but would also open up a new window to the universe that will revolutionize our understanding of the cosmos. Giant ears to detect these gravitational waves are currently being upgraded here in the US, in Washington State and Louisiana, as well as in Italy, Germany, India, and Japan. Before the end of this decade, we expect these detectors to reach their design sensitivities and observe the first gravitational waves. But how do these detectors work? After all, our science teacher Sigourney Weaver in the sci-fi lesson Alien has taught us that in space, nobody can hear you scream. Unlike sound waves traveling through air, gravitational waves do not propagate in a particular medium. They are undulations of the medium itself. They are undulations of space-time. So to understand how these detectors work, we must first understand how gravitational waves act on matter. When gravitational waves hit us, they shake things around, changing the distance between separated objects. Right now, there are gravitational waves passing through us, causing the distance between me and you to oscillate back and forth in a predictable fashion. The change is tiny, though, so we never notice it. To get to a noticeable size, we need the distance between us to be quite large. The detectors we've built to measure gravitational waves have arms that can stretch over 4 kilometers. Even in this case, the distance change we're looking for is about 1,000 times smaller than the size of a proton. This is too small for us to just place a microscope near a mass and look for the wiggles. Instead, we rely on a technique called interferometry, which exploits the fact that light is a wave. This technique was introduced by the physicist Albert Michelson more than 135 years ago, and he went on to win a Nobel Prize for his work with light. Interferometry uses the fact that light, like all waves, has peaks and troughs. You're probably familiar with this from watching water waves propagate after throwing a stone into a pond. If 2 waves encounter one another, the peaks and troughs combine in a special way. 2 peaks make a big peak. 2 troughs make a deep trough. A peak and a trough cancel out, leaving the wave flat. Now imagine the overlapping ripples you see when you throw 2 stones in 2 widely separated places in a pond. These overlapping ripples are the interference of the water waves. Gravitational wave detectors work by looking for interference of light rays. We send beams of light down 2 long arms of our detector, which are at right angles to each other. The light in each arm bounces off mirrors at their ends, travels back down each arm, and combines together. The detector is carefully designed so that, if nothing weird happens, the peaks of light in one arm line up with the troughs in the other. The waves cancel each other out. When nothing weird has happened, a gravitational wave detector's output is a boring, dark spot. But imagine a gravitational wave comes along. Remember, what these waves do is cause masses to shift around. They shift the positions of the mirrors, making one arm a wee bit longer and the other a wee bit shorter. The careful placement that led to the peaks and troughs canceling out is broken. We now find crests lining up with crests and troughs with troughs. Instead of a dark spot, we get a bright spot whose brightness varies as the gravitational wave's oscillation makes the arm's lengths vary from long to short and back. This is the variation our detectors are trying to detect. Our experiments can detect length changes that are about 1,000 times smaller than a proton. We now suspect that they are on the cusp of being able to find the gravitational waves that nature is raining down on us. People often ask, and what is that good for? One quick answer is that experiments like this would verify Einstein's theory in a regime previously unexplored, and that would help us get a clearer picture of how many black holes there are in our nearby universe and what they look like. In short, it would revolutionize our understanding of the universe. To this, some folks might still respond, and what is that good for? And then we might step back and think about how progress in science often makes it possible for us to have TVs, movies, cell phones, satellites, GPSs, microwaves, lasers, etc. The links between crazy ideas and real-world gadgets aren't always direct, and the connections usually aren't made quickly, but they are real connections nonetheless. But you see, this is not really the reason we do what we do. We do what we do because we are compelled to. We do what we do because we are explorers, just like Lewis and Clark and Neil Armstrong. We do what we do because our inherent and insatiable spirit of discovery drives us. And it is this same spirit that drives innovation, which later drives industry and the economy. And this is where science and art meet. It's in our desire to explore, our desire to create, our desire to communicate, our desire to move. And who said that we couldn't explain science with dance? In times of economic strife, we sometimes forget why we do what we do, and we're tempted to support the simplistic view of cutting science and art out of our schools, out of our universities, out of the budget. This would surely bring the budget down, but at what cost? A society that forgets its spirit of discovery and creation also forgets how to innovate, how to invent, how to communicate. During times like these, it seems more important than ever to think about the story of gravity. Over the past century, Einstein's crazy idea about space that can bend and ripple has led physicists to the heights of theoretical speculation about black holes, the Big Bang, and more, all the way to down-to-earth gizmos like the GPS navigation system. Einstein's crazy idea, his beautiful, beguiling theory of general relativity, literally helps us find our place in the world every single day.